Okay, so vertical circular motion still follows a lot of the same rules that uniform circular motion followed, but there's something that is different. And it is a fundamental difference, and that is that in uniform circular motion, the speed is constant. But in vertical circular motion, the speed is not constant. This is non-uniform circular motion because we can see that the speed of the tape, as I'm whirling it around, is clearly changing. Where is it going fastest? At the bottom. Where's it going slowest? Top, because gravity's involved now, okay? Gravity acted perpendicular to all the other stuff we did, so it didn't really play a part. Now it does, all right? And as a result, we're getting changes in the velocity of the object moving around and around. Since the speed of the object in the circle affects centripetal force, is centripetal force also changing as this thing goes around and around? Yeah, where do I need the most centripetal force? Where did you just tell me it was going the fastest? At the bottom. Okay, doesn't speed have an exponential effect on centripetal force? Okay, radius isn't changing, so obviously where it's going fastest is where I require the most centripetal force. All right. Now, this translates, and it'll translate very obviously when you ride the Mindbender, okay, when we go to West Edmonton Mall. That translates into you feel heaviest at the bottom of a vertical circle. Right? Because at the bottom of a vertical circle, gravity is trying to pull you out of the circle. Your inertia wants you to go in a straight line, and the only thing that keeps you from doing that is the track. So you push on the track really hard at the bottom of the loop, and the track pushes back, okay? And as a result, that's where you feel the heaviest. You aren't any heavier at the bottom than you are at the top, obviously, okay? But you feel a lot heavier at the bottom. Okay? Everyone okay with that idea? Okay. It would be the same as when I'm whirling this thing around the circle, it pulls hardest at the bottom. Okay. It actually, if you watch it at the top, it doesn't pull at all. Okay. You can see that the string goes slack. Okay. When I'm going over the top of the vertical circle, if I go just fast enough to keep it in a good circle, there's actually no tension in the string. Okay. Everyone with me there? Now, if I go faster, then yes, there is, right? There's tension in the string everywhere, and that's what the Mindbender will be like, okay? You're going to feel pinned to your seat, bottom of the loop, side of the loop, top of the loop. You're just going to be pinned in there, and you'll be, hoping you don't pass out. Some of you will. It'll be funny. We'll laugh at you, but not in a mean way. You will? I've seen that actually. Yeah. That anxiety just gets to people. Yeah. Okay. Yeah, the best one I ever saw, and please nobody do this. It only makes for a good story. It's not funny now. Well, it is funny now, but it wasn't funny then. Yeah, it was funny then too, but don't do it. Okay? We had these two students. They were both mine, boyfriend, girlfriend at the time, and the girlfriend didn't want to get on the ride. Boyfriend put her on the ride, strapped her in, pulled the thing down so she couldn't get off, and so they broke up that day. No way. Oh, Yahweh, of course that, Yahweh, and he totally deserved it because that was a jerk move. But she screamed all the way up. The only time she stopped was to inhale again, right? It was like a constant screaming all the way up, and then down the first loop screaming, and then she just got quiet because she passed out. Not on the way up, but like bottom of that first loop, she had done, head bobbing back and forth all over the place. Yeah, yeah. Don't do that. It makes for a funny story, but don't do that, okay? Okay? It's kind of a no means no kind of thing, okay? They don't want to get on the ride, they don't have to get on the ride. Okay? All right. So, with vertical circular motion, okay, we have to remember a couple of things. Okay? Some of those things are that yes, the speed is going to change, and as a result of that, the centripetal force is going to change as we move through the circle. Right? Now, the other thing we have to remember is that centripetal force is the net force. Okay? And we calculate net force using the vector sum of all forces. The only directions that forces can act in a vertical circle is into the circle and out of the circle. And that's it. That's where we get the formula for vertical circular motion. Centripetal force equals the forces in minus the forces out. Okay. So the challenge with vertical circular motion is essentially being able to draw a free body diagram and determining which forces are present, which ones are acting in, which ones are acting out, okay, and then put them in this formula, right? That's really all there is to it. It's a net force calculation, but the only two directions are in or out, okay? Everybody with me so far? Okay, so if we are looking at a vertical circle, okay, we'll be looking at a few different points on the circle, okay? Now, if you've probably seen people do this, right? The loop, okay? You can just, you put something through the vertical circle. You have to achieve a certain minimum speed in order to stay in the circle. If you're not going fast enough at the top, what happens? You fall out. Exactly, and that happened with the tape here, right? Like if I get this thing whirling, I'm way faster than the minimum speed right now, but if I let that thing slow down, right, it falls. If I don't get it going fast enough, it falls out of the vertical circle. There is a certain speed that this thing has to move at in order to stay in that vertical circle, right? And the same is true if you're doing the loop here, okay? This little smart car would have to be going a certain speed for a circle of whatever radius we're using, and radius affects it, okay? For that circle, there's a minimum speed for that car to stay in the circle, right? Everyone follow me there? Now, obviously, roller coasters don't flirt with this, okay? It would be dangerous to have a roller coaster that flirted with the minimum speed because it could get stuck, okay? Or it could be going slow enough that people actually fell into their harnesses, okay? Because any roller coaster that goes upside down has a shoulder harness of some type. The Mindbender has this thing that squishes down on top of you, okay? Some of them have the big thing that you pull down and clips down below, okay? Stuff like that. But there's some sort of shoulder harness to keep you from falling out, okay? So they would never flirt with that on a roller coaster because it would be very dangerous. People could break their collarbones or their necks or things like that. So they don't do that, all right? So I have to achieve a certain minimum speed depending on the radius of the circle, okay? And we found this morning, I've been telling people, yeah, I've seen people that like try to run, like physically like run one foot in front of the other through a vertical loop. Do you have to go pretty fast? Yeah, or the loop has to be really small. Okay, now I found a guy, his video, Damian Walters is his name, okay, who actually ran the loop. Now, I'm going to show you just part of the video, okay, because part of it is them kind of building the loop and whatever. It's kind of boring. And then there's him trying it, okay, and they put mats in it because he, doesn't get it right. And I still don't think that by the end, even though he manages to do it, that he's ever done it right, okay. But I'll show you what it looks like here. The key is getting that minimum speed. You have to run pretty fast. And remember, if you're running through a vertical loop, at some point you're running straight up and then upside down, right? Like, I mean, you try and run uphill, it's harder than running on the level, okay? Well, you run up the side of a vertical circle, you're running straight uphill, okay, for a little while. So it's different. Okay, so if we're looking at this vertical circle, what we have to understand are the forces that contribute to what's going on in terms of the change in speed and thus the change in centripetal force. So if we're talking about the bottom of the vertical circle, okay, at the bottom of a vertical circle, gravity pulls out because it's down, okay, and down is out of the circle at the bottom. The track, or if it's something on a string, the tension pushes back into the middle, okay, and then we would have that Fc would be the vector sum of these two forces. So that's the force in minus the force out. Okay? And that would give us our centripetal force. Obviously, at the bottom of the circle is where I'm going to feel the heaviest because gravity's trying to pull me out of the circle. My inertia wants me to go that way. And we learned yesterday that even though this is perpendicular, it's still a force that requires the circle to push back into the middle, right? So the circle, the track, or the tension in the string is counteracting both of these things. This gets bigger the faster I go. Everybody with me on that? Okay, so the faster I'm going, the heavier I'm going to feel at the bottom of this circle, okay? Because this isn't going to change. Force of gravity, that's not going to change depending on my speed, okay? That's just going to stay the same. All that changes is if I go faster, I have more inertia, and as a result, the track has to push harder. Everyone okay with that idea? Okay. So I'm most likely to black out at the bottom, okay? Because that's where my blood is going to want to leave my head the most, right? Because it's my inertia is out of the circle, okay? And when I'm at the top, I might black out at the top too if I'm going really fast, okay? But more than likely, the top is not the spot where I'm going to black out. Okay? All right, at the top, if I'm on the inside, so if I'm going through the loop, okay, doing the loop on the inside, gravity is pulling me down, and if I'm going just fast enough to stay in the circle, that's the only force. Because if I'm going just fast enough, I don't push on the track, so the track doesn't push back. If I'm going faster than I need to, then I do push on the track from my inertia, and the track pushes back, and I would have two forces acting in, normal force and gravity. Okay, so then this formula is still forces in minus forces out. It's just now, it's Fn plus Fg minus nothing. There are no forces out when I'm at the top of the loop. Okay? There's nothing that's acting directly out of the circle there. Everybody okay with that? All right. The last place that we talk about is the top of the vertical circle on the outside. Okay, this is, you've probably experienced this. If you went over like a bump in the road, okay, like not like a speed bump, but like a, kind of a small hill, you sometimes feel like, your stomach and your heart are kind of coming up into your throat a little bit, okay? That's because you're going over the top of a vertical circle, okay? And in fact, the big speed bump out here, okay, just outside here, is basically the top of a vertical circle. If you hit it fast enough, don't. Okay, if you hit it fast enough, could you launch yourself off of it? Yes, okay, don't. Okay, we did have students back the first year we were here, 2006, who did. And they totaled, like the car was a wreck, okay? Like the transmission hit the ground when they landed, yeah. Yes, it was like a little Hyundai, yeah, and they jumped it, and the car was full, there was like 5 of them in it too. It's just, yeah, it was stupid, okay? And yeah, so when the car came down, all that weight in it, and it just bottomed out, and it just, everything came off, right? So I don't care how jacked up your car is, don't use that as a ramp. But it is the top of a vertical circle, and if you went over it fast enough, then, Well, I had a few people say that they would try that. I would say don't. Okay. So if I go over this hill fast enough, I'll lose contact with it. Okay. If I lose contact with it, how do I feel? I feel weightless. I'm not weightless. I still have gravity trying to pull me back into the circle. Okay. It's just now my circle is a projectile arc. Okay, I don't feel any weight because there's no normal force anymore, and I'm experiencing apparent weightlessness. Inside, right? Yeah. This is on the outside now, right? So as I go over the top of a vertical circle, not under the top, over the top, even under the top, if I go just fast enough, I still feel weightless. I don't really notice it as much, okay? But going over the top, it's much easier to make that feeling happen, okay? Or give that experience of apparent weightlessness. In fact, it's how NASA's Vomit Comet works. Okay, they just have a plane that flies in these parabolas, and every time you go over the top of one of them, you're weightless or apparently weightless. If the spinning does like drop people to the center, then how come during that like merry-go-round video we watched, people just flying out? Because that was horizontal. Oh, right. Right, it was uniform circular motion. This is vertical, so gravity is pulling them down into the middle. Yeah. No, you'll feel heavier. Not you're falling more, you'll feel heavier because you'll push on the track, and the harder you push on the track, the harder the track pushes back. When you ride the Mindbender, you're going to be pinned to the seat, top, bottom, doesn't matter, okay? Because you're going way faster than you need to go to stay in one of those loops, like way, way faster. All right, is that making some sense? Okay, but if I go over the top, okay, if I go, just kind of a reasonable speed, then yeah, I'm going to push on the ground, and the ground will push back. Gravity will pull me in, okay? And I'll still have this forces in minus forces out thing going on. It'll just be force in minus force out. Okay? Eventually, though, I might get to the point where I go fast enough that Fn becomes 0. If that's the case, then I'm a projectile again. Okay, and we know that for all projectiles, the thing that makes them follow that arc is gravity. Okay, and this is why the guys on the International Space Station are apparently weightless. They're not really weightless. Okay, they're still attracted to the Earth. Okay, in fact, they're always falling towards it. That's why they're apparently weightless. Okay, all an orbit is a projectile arc that never encounters the ground. It actually completes the circle. Okay, so to make something orbit the Earth, what you do is you make it go fast enough that the distance it falls is equal to the distance the Earth curves away from it, so that it can always fall but never get closer to the Earth, and thus it orbits. Okay, so the International Space Station is just a projectile. It's always falling. Okay. So if you had something fast, launch yourself around the Earth. No. That's theoretically, yes. Practically, no, because you'd have to go almost 8 kilometers per second, which would instantly vaporize you. Okay, that's why things burn up when they hit the Earth's atmosphere, right? The faster you go within the Earth's atmosphere, the more friction there is. Like when the the SR-71 Blackbird, that spy plane that the Americans had that was like really, really fast, the pilots couldn't get out of that when it would land. It would be so hot that they had to wait for it to be cooled before they could get out. Okay, and it's the same for the space shuttle. When it would come in, right, all the little ceramic tiles on the bottom would get like cherry red hot. Okay, and then when it would land, okay, they would have to cool the ship down in order for the people to be able to come and bring the ladder over and all that kind of stuff. It's just hot because of friction. You mean to get into orbit? We're actually going to go over that in a couple of days. But it ends up being this. It ends up being centripetal force provided by gravity, and you just solve for V. But just not m times g. It'll be Newton's universal law of gravitation, which we haven't taken yet. But we will be talking about exactly how you figure that out.
How can we say that space actually has like zero gravity if we've never actually been in like a zero gravity environment? We've been to like a parent.
Well, because zero gravity is just it's not truly the absence of gravity. It's zero apparent gravity. Right? So we say 0g because I feel a force of 0 g's, right? I'm actually still having like 1g or a little less than 1g at low Earth orbit, right? If I was to be out in interstellar space, the furthest distance from any two objects I could possibly be, I still wouldn't be in 0g. I'd still be attracted to something gravitationally. There's always a gravitational force pulling.
But like, it doesn't, if you were like trillions of light years away from any like body or object anywhere, you could still be.
Yeah, the force might be incredibly small, but there would still be some attraction.
There's never a point where it's too far away and it just becomes zero.
It'd be pretty hard anywhere in the known universe to be that far away from anything else, right? Like there's always matter, and as long as there's mass, there's gravity. Okay, like the thing we haven't talked about is this: Newton's universal law of gravitation says that the force of gravity between any two masses, okay, is affected by the masses of those two objects and the radius between them. Okay, now this is inversely exponential. So if I double the distance between the two objects, the force of gravity between them is 1/4. Right? If I triple the distance, it's 1/9. It's inversely exponential. Okay, but remember, there's a lot of mass in the universe. Right? When we're talking about the sun, okay, like that's a huge number. Okay, or a supermassive black hole. One of these numbers is a huge number, okay, and that can affect this as well. Yeah. Okay. So if I get into low Earth orbit, R is bigger, and so I'm not feeling the same weight I would, but I'm still attracted to the Earth. Okay, that's why the Moon orbits the Earth. It's a long way away, but it's big. The Earth is big, right? This distance is big, but not outrageous. Yeah. Okay. All right, so back to this vertical circular motion stuff here. Okay, I'm going to show you a couple of videos here. The first one is going to be from Cirque du Soleil, from Cirque du Soleil Cusa, where they have the double wheel of death. Okay, it looked, oh yeah, it's cool. Okay, it's basically like two hamster wheels, and these guys like rotate this thing and they get it going, and you can actually see the stuff we've been talking about, which is, you know, when they feel this apparent weightlessness. Okay, when they become a projectile versus part of the circle, when they're heavier, okay, things like that. You can actually see it in how they move within this wheel as they make it spin. Okay, these two guys are incredibly athletic to be able to do this. It's a lot of running, it's a lot of pushing, okay? But it looks really cool. Okay, and we haven't talked about this, are the sides of the circle. Okay, now on the sides of the circle, we never do any problem solving to do with those because they're exactly the same as for uniform circular motion. Okay, gravity is perpendicular to the movement at this point, so it doesn't play any part. The only centripetal force is either the string or the normal force. Okay, the gravity doesn't play a part on the two sides. Okay, so we only ever deal with top on the inside, top on the outside, bottom on the inside. Okay, why don't we deal with bottom on the outside? Yeah, you can't, right? Now, I mean, you could build a roller coaster like this because roller coasters have two sets of wheels, right, that squeeze a pipe in between them so that it can't fall off the track. Okay, but you couldn't make one that just sat on top of the rails and did this because it'll fly off. Okay, the other reason is even if you had the two-wheel system that squeezes the pipe, you'd kill people with this. Okay, because if you're here, you're pulling positive g-forces. That is, you feel heavier and the blood rushes away from your head and you black out. Here, it's the opposite. The blood rushes to your head. These are what we call negative Gs, and they're deadly. Okay, the human body can withstand huge positive Gs for even fairly sustained periods of time. We can sustain 4 negative Gs for only a few seconds. Okay, because if we do, it'll cause an aneurysm. Okay, some sort of brain bleed because all the blood will rush to our head and the little delicate capillaries in our brain will rupture and be like having a stroke. Whatever part of the brain was fed by that blood vessel is now no longer being fed. You're bleeding into the brain, which causes swelling. Okay, and then they have to do like the subdural hematoma where they drill holes in your head, in your skull to relieve the pressure on your brain. Okay, so we're not going to build roller coasters like this because they'd kill people. Okay, and similarly, fighter pilots never fly the bottom of a loop inverted because it'll kill them. Okay, they're flying the bottom of a loop; it's always upright. Okay, they might black out. Okay, but probably not because they're highly trained. But if they flew it inverted, it would kill them. Okay, so they have to be very mindful of that as well. Pulling negative G's can be very deadly. All right. Okay, making some sense? All right. Now, what I'm going to show you here is kind of this. We've talked about this here. The formula for vertical circles is forces in minus forces out. It's not on your formula sheet because it's net force. Okay, it's the vector sum of all forces, and we just have to remember that. But we generally write it as forces in minus forces out. Okay, this is apparently like a real track that somebody built, and then they run real cars through it. So if you ever had those orange Hot Wheel tracks when you were a kid, okay, yeah, this is like the real thing for when you grow up, okay, and you want to drive your real car through there for some reason. Okay, you could do that. Yeah, it seems perfectly safe. If you go fast enough, it is perfectly safe, as long as you don't lose it. Yeah. Yeah. Well, yeah, if you hit one of those, it would slow you down and you'd fall out of the circle. So don't do that. All right. Now, the other thing I'm going to show you here is what the vertical circular motion, the Vomit Comet thing, how that works. Okay, how people feel apparently weightless when they do that. This music group called OK Go actually made a music video that they filmed entirely in this zero gravity trainer. Okay, it looks really cool. Okay, what they did, and then they have a how did we do it, how did we pull it off kind of video. Like this group, has anyone ever heard of them? OK Go. All their music videos are like mind blowing. Okay, they plan them out intricately, and they all involve some sort of timing or physics or something like that. And their videos are insane to watch. Okay, I mean their music's, but you know the stuff that they do in their videos is just unreal. And this one here is again filmed all in the vertical circular motion zero gravity trainer. All right, so if you're going to do this loop-the-loop trick, okay, like we were talking about, then you have to have that minimum speed, okay, that you attain at the top of the circle. When you're at that minimum speed, we have to remember you are only going to be using gravity as your centripetal force. You go any faster than that, you're going to add normal force to that. You're only going to have those two forces acting in. If you're going over the top, you got gravity acting in, normal force acting out until you go fast enough that you lose contact with the surface, and then you have no normal force and you are thus apparently weightless. Okay, so that is one term that we have to remember. Okay, and they're going to use it a lot in this unit. Apparent weight is normal force, okay? Because it's very easy to get a vertical circular motion question that says, you know, the person is moving this fast in a circle and their apparent weight is this many newtons. And I have to remember that that means that's the normal force, okay? I can always calculate their actual weight if I know their mass, okay? And I might be solving for, you know, how fast they're going or the radius of the circle or something like that, okay? Everyone with me on that? Okay, now I'm going to show you a roller coaster video because it's just funny. Okay. No, no. The video doesn't work anymore. Okay, so here's what we want to do first. We want to calculate the minimum speed required for a roller coaster like the one we just watched to go through an Immelman, that's a vertical loop, okay? If the radius of the track is 9 meters, all right? So this is minimum speed now. We have to remember that that means I'm going just fast enough to stay in the loop. So I don't push on the loop, and the loop doesn't push back. So that means when I draw my kind of free body diagram here, that I only have gravity acting as a force, okay? So for all vertical circles, centripetal force equals the forces in, gravity, minus the forces out. There aren't any. So this is what I'm left with. Fc equals Fg, which is true. If I'm only going the minimum speed, I'm a projectile. Okay, I'm not utilizing anything else to keep me in that arc, just gravity. Okay, so we got mv squared over r equals m times g, which is basically like what we were looking at for the artificial gravity questions the other day. Okay? And in fact, gravity acts as a centripetal force so often that if I was like totally lost and had no idea how to solve a problem on a unit exam, I would write that because probably 1 out of every 4 times that's the right way. Okay, it happens that often. Okay, that gravity acts alone as a centripetal force. Okay, that's only if you were totally lost. I'm not saying like guess that way every single time. Okay. All right. So what I'm looking for here is what's the minimum speed. So I'm trying to solve for v. So I'm going to multiply both sides by r. M's going to cancel when I divide both sides by it, and then I'm going to take the square root. So this is exactly like our artificial gravity question from the other day. The speed of the spinning drum was the square root of g, okay, which is what we've got here for the minimum speed. So that'll be 9.81 times 9 meters. That was the radius of our loop. All right, so we're looking at 9.4 meters per second as our minimum speed. All right, so are you going to be able to run this loop? No, you would never be able to run this one. Okay, 9.4 meters per second at the top of the loop. Okay, you might be able to run 9.4 meters per second on level ground, but not running straight uphill. Okay, all right, so that's why we'd have a roller coaster doing this instead. Okay, you may. Go ahead. Okay, so does that make sense to everybody how that one works? Okay. Okay, so we said minimum speed, this is the math we just did, v squared equals the square, or sorry, v equals the square root of rg, okay, and then that's the answer we got there. All right, so we're going to go through a couple of example problems here just to kind of work through how this kind of sets up, look at some of the different situations, okay, but let's maybe look at one like this for a second. So copy this one down as an example. Actually, I think I have it here. Okay. So how fast is this roller coaster moving if the radius is 12 meters and a 65 kilogram person feels an apparent weight, which is normal force, of 200 newtons. So now we're going over the top of the vertical circle, okay? This person only feels like they weigh 200, okay? They actually weigh quite a bit more than that, but they only feel like they weigh 200. We want to figure out how fast the roller coaster is going. I'm going to give you a couple minutes, see if you can solve that, then we'll walk through. Okay, so if we're looking at this situation, we're on the top of a vertical circle. We're told they do have an apparent weight, which means there is normal force acting out of the circle. Obviously, there's gravity acting into the circle. Okay, so now we can set up our Fc equals forces in minus forces out calculation. Fc is going to equal m times g, or the force of gravity, minus the normal force. Okay, and so if I'm starting to plug in my formulas here, that's going to be mv squared over r, that's our FC, equals m times g minus 200 newtons, right? Because they actually told me what the value for Fn is. So I'm trying to figure out how fast the roller coaster is going. So I've got to solve for v. So the first thing I need to do is move r. How do I do that? Right, but I'm going to need to do this first. Okay, I'm going to multiply both sides by r, and then I'm going to divide both sides by m. Will m cancel this time? No. Right, it's not, yeah, there's another operation up here that comes first, so m does have to come over and not cancel, and then I need to square root. So that means there's a little bit of algebra here, but it's nothing you guys can't handle. Okay, the biggest part of this is identifying the forces and getting them into this equation here. Okay. So when we're plugging in our numbers, we're going to have that V will equal 65, the mass of the person, times 9.81 minus 200 newtons times 12 meters, the radius, then divided by 65 kilograms, the person's mass. Come on. Lots of brackets. I'm not going to do it that way. 65 times 9.81, because I tried to do it that way this morning and I embarrassed myself. Okay. Minus 200, okay, times 12, divided by 65, square root. All right, so we're looking at 8.99. I think we had 3 significant figures there, right? Just 2? 9. 9.0 meters per second, okay, is the speed that this roller coaster must be moving at in order to make that person feel considerably lighter than normal. Okay, everybody all right with that one? All right. Something else that occasionally comes up in this unit is the mention of G-force. Okay, G-force is a ratio. It always is. Okay, and G-force is the ratio between your apparent weight and your real weight. All right, so if you're pulling 2 G's, you feel 2 times heavier than normal, meaning Fn, your apparent weight, is 2 times greater than your actual weight. All right, so anytime you see G-force, this is how it's calculated. Normal force divided by the force of gravity. I don't use that term very often in like problem solving, but it does come up occasionally, so just be ready for it. G-force is just the ratio between normal force, your apparent weight, and your real weight. Okay. All right. No, we're not going to do that one. Okay, I want you guys to try this one. It's the bottom of the vertical circle this time. Okay, now in this case they've got like a bucket on the end of a rope, so they're talking about tension, but tension and normal force work exactly the same. All right, if you have a track, you have normal force. If you have a rope, you have tension. It's a force at the bottom at least that acts back into the middle. All right, so see if you guys can calculate the tension in this rope based on this situation. Radius is 0.75, mass is 1.5 kilograms, speed is 3 meters per second. Okay, see if you can calculate what that tension would be. Forces in minus forces out equals FC. Okay, I'll give you a couple minutes on that one. So we're dealing with bottom of the circle. They've already drawn the free body diagram for us. We know that gravity is acting out and the tension is acting in. So we start out with FC equals forces in, tension, minus forces out, gravity. Since I'm looking for the tension in the rope, what do I have to do with gravity? Add it, right? Do the opposite. So I'm going to have FC plus FG equals T. And that should kind of make sense intuitively because this is where I would feel the heaviest or where I'd feel the rope pulling the hardest because gravity is pulling against me at that point as well as my inertia and all that other stuff. Okay, so now I can plug in my formulas. mv squared over r plus m times g gives me tension. I just put in my numbers, right? So it was a 1.5 kilogram pail times 3 squared divided by the radius, which was 0.75 meters. And I'm going to add that to 1.5 times 9.81, the weight or the force of gravity acting on it. Okay, so we got 1.5 times 9 divided by 0.75. Okay, and then we're going to add that to 1.5 times 9.81. Okay, so the tension in the rope is going to be 32.7 newtons. Okay, everyone follow what I did there? Okay, just manipulating the forces around. It's really just a net force calculation, right? Forces in minus forces out gives us our net force into the circle.
When we draw free body diagrams, do you want us to draw a circle as part of it, or do you just want to be on?
I would say probably draw the circles here, indicating to me where that you know where on the circle we're talking about. Yeah. Okay, I think we'll leave it at that. I'm going to show you one.